Welcome to Module 3. In this module, we will discuss limits. Let's jump right in. Consider a circle that has radius 1. We know from modern formulas that the area of the circle is a equals pi times r squared, which would be pi times 1, which is just pi. Now pi is approximately 3.1416. Before anyone knew about the value of pi, the Greeks used a series of approximations to estimate the area of the circle by inscribing a series of polygons inside of it. If we inscribe a polygon with 3 sides, which is just a triangle, we can easily find the area to be 1.299. A polygon with 4 sides has an area of 2. 5 sides gives an area of 2.3776. 6 sides gives an area of 2.5981. Let's look at a polygon with 10 sides. We find this area to be 2.9389. With 20 sides, the area is 3.0902. When we have 100 sides, the area is 3.1395. And finally, if there are 500 sides, the area is approximately 3.1415, which is really close to the value of pi. Now you can imagine if we keep going, the area of the inscribed polygons would get closer and closer to the value of pi, as the number of sides gets larger and larger. In calculus, when one variable approaches a fixed number as another variable changes, we have what is called a limit. Here, we would say that the limit of the area is pi as the number of sides increases. Let's take a look at another example. Suppose that $10,000 is invested in an account that pays 5% interest. If the interest is paid annually, the amount in the account after 10 years is a equals 10,000 times 1 plus 0.05 raised to the 10th, which is 16,288.95. Now, if the interest is paid more than once per year, then the investment would be more. Let's say that the interest is paid n times per year. Then the amount in the account after 10 years would be a equals 10,000 times 1 plus 0.05 over n, all of this raised to the 10 times n. Let's take a look at the effect that n has on the investment. If the interest is paid annually, which is 1 time per year, we have $16,288.95. If it's paid semi-annually, which is 2 times per year, we have $16,368.16. Quarterly, which is 4 times per year, yields $16,436.19. Monthly, which is 12 times per year, gives us $16,470.09. Daily yields $16,486.65. Hourly yields $16,487.19. Minutely yields $16,487.21. And finally, secondly yields $16,487.21. Notice that it appears that the limit of the investment is $16,487.21 as the number of times the interest is paid increases. Let's take a look at the definition of a limit. The limit as x approaches c of the function f of x equals L means that as x gets closer to the number c, then f of x gets closer to the number L. Now let's be careful here. We aren't saying that we care about what happens when x equals c, we only care about what happens when x gets closer and closer to c. Let's look at an example. In this example, I wish to evaluate the limit as x approaches 2 of x squared minus 4 over 5x minus 10. And I'm going to do this numerically in the calculator. Now I've already entered my function into the calculator as y1 equals x squared minus 4 over 5x minus 10. Now I want to set up a table. So I'm going to press second window, which takes me to the table setup, and I'm just going to change the independent variable here to ask. So it's asking me to put in different values, and it'll give me the y values. I'll press second graph, which takes me to the table. I'm going to start by putting in some values that get increasingly closer to 2, but they're going to be less than 2. So I'll try something like 1.9, which gives me 0.78. 1.99 gives me 0.798. 1.999 gives me 0.7998. And we see that these numbers seem to be getting closer to 0.8. Now let's put in some values that are a little bit more than 2. How about 2.1, which gives us 0.82. 2.01 gives me 0.802. 2.001 gives me 0.8002. And again, these values seem to be getting closer and closer to 0.8. Now let's take a look at this graphically. Here we have the function x squared minus 4 over the quantity 5x minus 10 graphed. Now let's see what happens as x gets closer and closer to 2 coming from the left. So we're getting closer and closer, and we see that the y value here gets closer and closer to 0.8. Now let's see what happens when we go towards 2 coming from the right. Here we have values like 2.006, so we're getting closer and closer to 2, and the y value again is getting closer and closer to 0.8. Now when x equals 2, we see that the y value is undefined. That's because with 5x minus 10 in the denominator, x can't be 2 because that would give us a 0 in the denominator. But with limits, we don't care what happens when x equals 2, we only care what happens when x gets infinitely close to 2. Here is a rule that will help us evaluate limits. Doing algebra on a function does not change the value of the limit. So let's look back at the example again. Again, we're trying to evaluate the limit as x approaches 2 of x squared minus 4 over 5x minus 10. Now we see here that we can do some algebra on this. I'm going to rewrite this as the limit as x approaches 2. And in the top, that's a difference of squares, so I can rewrite that as x minus 2 times x plus 2. And in the denominator, I can rewrite this as 5 times x minus 2. And we see here I have x minus 2 in the numerator and in the denominator. And so I'm going to cancel those out. And remember, I can do that because x is not equal to 2 here. X is only getting closer and closer to 2. And so I'm left with the limit as x approaches 2. I have x plus 2 in the numerator, and I have 5 in the denominator. Well, now if I try to take 2 and put it in here, it looks like I get 4 in the numerator and 5 in the denominator. And if I want to write that as a decimal, I get 0.8. And so the limit as x approaches 2 of this function is 0.8. Consider a couple of more examples. In this problem, we're going to evaluate the limit as x approaches negative 2 of x squared minus x minus 6 over the quantity x plus 2. And we can see here that if we tried to stick negative 2 in place of x, we will get a 0 in both the numerator and the denominator, which isn't going to help us find out what the limit is. So let's try some algebra. I'm going to rewrite this as the limit as x approaches negative 2, and looks like I can factor the numerator. That would be x minus 3 times x plus 2, and I still have x plus 2 in the denominator. And we can cancel out the x plus 2 in the numerator and denominator. And when I do that, I see I get the limit as x approaches negative 2, and all I'm left with is just x minus 3. And so now there's no problem with putting negative 2 in place of x. We end up with negative 2 minus 3, which gives us a limit of negative 5. Let's look at another example. We want to evaluate the limit as h approaches 0 of the quantity f of x plus h minus f of x all over h, where f of x is equal to x squared. Okay, so obviously if we were to just put 0 in place of h, I would get a 0 both in the numerator and the denominator. So we have to do some kind of algebra here. Well, let's go ahead and evaluate these functions because we know that f of x is equal to x squared. So we're going to get the limit as h approaches 0. Now f of x plus h, where f of x is equal to x squared, would give us x plus h squared. And we're going to subtract off f of x, which is just x squared. And all of that goes over h. Well, now let's see if we can expand this out some. I'm going to rewrite this as the limit as h goes to 0. Let's see, x plus h squared, that would just be x plus h times x plus h, which is going to give me x squared plus 2xh plus h squared. And we're subtracting off x squared up here. And all of that goes over h. Well, it looks like we can cancel x squared and negative x squared, which gives us the limit as h approaches 0, and what we're left with is 2xh plus h squared in the numerator, and in the denominator I have h. Well, it looks like we can take this one step further. Limit as x approaches h, if I factor in h out of the top, I'm left with 2x plus h, all that over h, and now these h's can cancel out. So I have the limit as h approaches 0, and what I'm left with is 2x plus h. And now if I let h equal 0, this entire thing just gives me 2x. And so the limit is equal to 2x. Here is a strategy tip. Try simple substitution first. If problems arise, then try using algebra to rewrite the expression. Consider another example. In this example, we want to find the limit as x approaches 4 of x squared minus 2x minus 3 over x plus 6. Now our strategy here is to try simple substitution first. And we can see here that if we substitute x equals 4 into x squared minus 2x minus 3, we're going to get some number up here in the numerator. And if we put a 4 into the denominator, we get 4 plus 6, which is going to give me 10 in the denominator. And so it appears that we could find this limit just by substituting 4 in place of x. So we have 4 squared minus 2 times 4 minus 3 all over 4 plus 6. And that's 16 minus 8 minus 3, which gives us 5 in the numerator, and we get 10 in the denominator, which gives us 1/2, or 0.5. What we've been looking at so far are general limits, where we've been looking at approaching a number from both sides. Now let's talk about one-sided limits. The limit as x approaches c from the left has the following notation, where we have a negative sign as a superscript to the number c. The limit as x approaches c from the right has this notation, where we have a plus sign as a superscript to the number c. Now the general limit exists if and only if the left-sided limit equals the right-sided limit. Let's look at some more examples. In this example, we're trying to evaluate the limit as x approaches 1 coming from the right of f of x, where f of x is defined as a piecewise function. F of x is equal to x plus 2 if x is less than or equal to 1, but it's equal to 2 minus x if x is greater than 1. Now if we're approaching 1 coming from the right, that means that we're talking about values that are greater than 1. And so we're looking at this bottom definition of f of x. So if x gets closer and closer to 1, then the quantity 2 minus x will also get closer and closer to 1. So it appears that this limit would be 1. We can also look at this graphically. Here we have the graph of the piecewise function, and we're interested in what happens when x gets close to 1. And we'll start by looking at what happens when x approaches 1 from the left. As x approaches 1 coming from the left, we see that the y values approach 3. However, as x approaches 1 coming from the right, the y values seem to approach the value 1. Now one thing to note here is that we can see that the general limit as x approaches 1 does not exist in this problem because the limit coming from the left is not equal to the limit coming from the right. Consider another example. In this example, we wish to evaluate the limit as x approaches 5 of the square root of x minus 5. At first glance, this may seem like a pretty straightforward problem. If we substitute x equals 5 in here, we get the square root of 0, which is just equal to 0. However, we have to be a little bit careful. Remember that a general limit only exists if the limit coming from the left is equal to the limit coming from the right. Let's first evaluate the limit coming from the right. Well, if we are approaching 5 from the right, we're talking about values that are just a little bit greater than 5. And we can see that if we put values a little bit greater than 5 in place of x, and they get closer and closer to 5, then the expression under the square root would get closer and closer to 0, and the whole thing would approach 0. Well, now let's consider the limit coming from the left. This means that we would substitute values that are increasingly close to 5, but they would be a little bit less than 5. However, if we put a value less than 5 into this expression, then we would get a negative underneath the square root, which is not equal to a real number. And so we can see that the limit coming from the left doesn't exist. Now, since the general limit only exists if the limit coming from the left is equal to the limit coming from the right, we see that the general limit here also doesn't exist. Next, we'll talk about limits at infinity. Long-term behavior is often a matter of interest in business, economics, or information technology applications. For example, a business manager may wish to know the average cost of producing a product as the level of manufacturing increases infinitely. Or a programmer may wish to know the stability of a section of code as it is run open-ended. The symbol infinity is used to represent unbounded growth. When we write the limit as x approaches infinity of f of x equals L, this means that the function f of x approaches a number L when x grows infinitely large. Limits at infinity often result from rational functions in the form g of x over h of x, where g of x and h of x are polynomials. To evaluate the limit as x approaches infinity of g of x over h of x, there are two cases to consider. If the highest exponent of g of x is less than the highest exponent of h of x, then this limit equals 0. If the highest exponent of g of x is equal to the highest exponent of h of x, then this limit is the ratio of the leading coefficients. Let's consider another example. A computer virus is spreading through the network at an organization. The number of computers infected t hours from now is modeled using the function n of t equals 400t over the quantity t plus 100 minus 500 over the quantity t plus 1000. All of this plus 0.5. What is the expected number of infected computers in the long run? That is, as t approaches infinity. I'm going to consider the second term of this expression first. We can see that the highest exponent of t in the numerator would be 0. There is no t up there. The highest exponent of t in the denominator is 1, so we have an expression where the highest exponent in the numerator is less than that of the denominator. And so we know this whole term heads off towards 0 as t approaches infinity. Now let's look at the first expression. We have 400t over t plus 100. The highest exponent of t is 1 in both the numerator and the denominator. So the limit of this term would be the ratio of leading coefficients, which would be 400 over 1. So when we consider the entire function, the first term gives us a limit of 400, the second term is a limit of 0, and the third term is 0.5. So the entire limit equals 400.5. The expected number of infected computers in the long run is 400.5. In this video, we've discussed limits. The concept of limits forms the cornerstone of calculus, bridging our intuitive understanding with mathematical precision. Whether we're approaching a specific point or stretching towards infinity, limits provide a powerful tool for grasping the essence of continuous change, which is really what calculus is all about.